Sir, can we start the session, sir? After a small introduction about your...
Sure. I'm ready.
Okay, sir. Thank you, sir.
Good morning to all. It's an honor to have with us the Honorable Chief Guest, Dr. Manu Santhanam Sir, a professor from IIT Madras. Dr. Manu Santhanam Sir is a professor in the Building Technology of Construction Management Division and currently the head of the Department of Civil Engineering, IIT Madras. He completed his bachelor degree in IIT Madras and master's program and doctoral research work in Purdue University. Professor Manu Santhanam Sir joined Sika Corporation, USA as senior in R&D and served for more than 2 years. He is also a part of the National Center for Safety of Heritage Structures. He is actively involved in several research projects funded by government and private agencies on the design for self-compacting concrete. He has co-authored more than 170 publications on construction materials. He is also active in various professional associations such as ACI, ICI, and RILEM. He has been working on developing 3D printing technology in the area of 2016 and developed the complete source 3D printing construction technology successfully. It aims to develop a platform and a specific process to a miniature single-story house of 320 square feet within 3 days. A prototype structure has been printed in IIT Madras and serves as a foundation model for accelerating R&D. His awards and honors are Professor V. Ramakrishna Award for Young Researcher in Concrete Technology in the year 2006, Young Engineer Award in the year 2008, Tamil Nadu Center Ultratech Award for Outstanding Young Concrete Engineer in the year 2007, FOSIC Award for Outstanding Concrete Technologist in the year 2018. Its research areas are ultrasonic imaging of concrete, use of lower grade limestones in concrete, optimization of 3D printed concrete. Thank you so much, sir. Now I will hand over the session to you, sir.
Thank you very much for that kind introduction and good morning to all the participants in this interesting faculty development program on digital transformation in the construction industry. Of course, there's a lot of things that are happening in the construction industry that previously were unthought of. Today, we want to move towards productivity levels that are typically achievable only in the manufacturing realm. One never thought about these kinds of productivity levels in construction. Many new technologies like rapid construction methods, tunnel form, your MyVan, all these kinds of new technologies have come up in the last 10 to 20 years and have really revolutionized the rate at which we do construction. One such new potential technology is 3D printing, which makes it possible for you to produce complicated structures and forms without the need for any form work, and in the end helps you save considerable amount of time and cost. So my objective in today's interaction would be to help you understand what does it take to actually build using 3D printing and what are the challenges ahead to really meet the demands of housing in our country. So let me share my presentation here. Okay, I hope you're able to see my full screen.
Yes, sir, it's visible, sir.
Okay, good. Thank you. So the title that I've given to this talk is Creating a New World Through Concrete 3D Printing. Now, 3D printing is something which is conventionally done in manufacturing industry. They do a lot of 3D printing. And today, of course, in terms of medical aspects also, there's a lot of 3D printing being done. In fact, people have even printed biological tissues and used them for replacement inside the human body and things like that. So 3D printing is quite an advanced technique in many of these realms. But as far as construction is concerned, we are still in the research stage. It will take some time for us to really come out to the industry in a large way. Nevertheless, there is potential, and that's what we set out 4 years ago to realize what kind of potential might be there in 3D printing. In the company of this group of students who had graduated from IIT, who formed their own construction or who formed their own startup company called Twasta Manufacturing Solutions. Twasta is made up of several of IIT Madras graduates, not from civil engineering per se, but primarily from manufacturing areas, material science and manufacturing. So they set this up, and then now, of course, they are looking a lot on construction 3D printing. So together with IIT Madras, TWASTA has created what is known as the IIT Madras Printability Lab, or Imprint. So that's the lab under the auspices of which we are doing most of the work that you'll see being reported today in the presentation. First of all, what is 3D printing? Okay, now in manufacturing terminology, we often call something as additive manufacturing when we deposit material layer upon layer. Okay, so that essentially is 3D printing. When you try to remove material from a larger block by machining it, like milling, turning, grinding, water jet cutting, and sawing, these are techniques that are called subtractive manufacturing. You are basically creating an object from a larger object by removing things. Okay. Now, for obvious reasons, subtractive manufacturing will have a lot of wastage, which can be minimized as far as additive manufacturing is concerned. Now, of course, mind you, with concrete, it's always additive manufacturing, right? We put the formwork in place and we put concrete inside. We don't really make a large block of concrete and then start cutting it off. That's not the intention there, right? We always have additive manufacturing in concrete, but can we do the same manufacturing of the concrete wall or column or beam, etc., without the need for a formwork? And that's where the challenge of additive manufacturing in terms of 3D printing actually comes in. So in construction, 3D printing is typically accomplished using two types of processes. One is called extrusion-based 3D printing, where the material, the concrete basically, is extruded through a nozzle, which puts some pressure on the concrete and extrudes it in the desired shape. And this concrete is actually deposited layer upon layer to create the entire structure. Okay. Now that again can be accomplished by two types of robotic systems. One is called a frame-based system, which you see here in this picture. There's a frame here. There's a gantry which is moving on this frame, and the Z-axis of the gantry is basically carrying the nozzle, and the nozzle basically does the deposition, while the printer can move in all three different axes. You could also have a robotic arm-based system where you have a single robot in the center of the room and which can print everything around it. So that's called a robotic arm-based system. You can also adopt a different technique called binder jetting. Now, this is a little bit more complicated to produce larger structures with it, but it can be very important to produce intricate, smaller structures like scale models and things like that. So here what we actually end up doing is we put a layer of, let's say, sand on which we can then put a polymer in the desired shape of the object. Or if you want to take it as concrete, we can put cement mortar in a bed and spray water on it in the shape that is desired for the object, and have successive layers of cement mortar laid on top, and water can be placed on those locations to give you the desired shape. But there's a lot of cement mortar around the desired object which will go waste, and that has to be removed or reused for the next process. So it's a little bit complicated to use binder jetting for conventional construction. So that's why usually whenever people around the world are talking about 3D printing, they are essentially referring to the extrusion-based 3D printing systems. So where the material is extruded through a nozzle, much like how we make murukku, right? What we do there is we prepare the dough, we put it inside the mold and simply press it out, and it comes out in the desired shape. That's exactly what we're doing with 3D printing. Now you can imagine that the concrete that needs to be pressed and pushed out of a nozzle has to have distinctive properties which make it possible for getting printed, and the printed material also retaining its shape in the proper fashion. So again, here we're talking about concrete characteristics that have to be defined very carefully and have to be properly addressed by the use of specialized materials inside the concrete. Now, from the construction viewpoint, additive manufacturing is very useful because we can reduce construction time and cost considerably. How do we do that? Primarily because we don't need formwork anymore. Many of you who are in construction management can do calculations to show that the use of formwork is responsible for nearly 40% of the construction cost and 60% of the construction time. And that's a substantial amount of time just for putting together formwork and removing it, right? And this time can be saved almost entirely by the use of 3D printing. Okay. Second and most important thing is that you can actually achieve shapes which are not possible with conventional formwork. For instance, when you're trying to make shapes like circle or curved walls and intricately designed walls, these kinds of things are not possible with simple formwork systems. You need to really complicate your formwork and ensure that you're able to print forms that can take the shape that you desire to create. In 3D printing, that is possible. You can actually now start creating shapes that were not conceivable with conventional formwork-based systems. Now, 3D printing around the world has become really popular, all the way starting from about 2005 onwards. There have been several efforts around the world in 3D printing. People are even talking about using 3D printing to print bases on the moon and Mars. You can imagine the extent of research that people have been doing on 3D printing for a long period of time. These are some of the common manufacturers of 3D printers across the world and who have been doing extensive work. I was talking about the robotic arm system. This is what it looks like. It's a robot, and the robot can actually move around itself in several different locations. Okay. All the others that are shown are frame-based printers. All these are frame-based printers. This is the printer that Twasta manufactured. Okay, this is the printer manufactured by Twasta, which we are using for our 3D printing operations at IIT Madras. Again, it's a frame-based printer, and you can see the gantry here with the movable Z-axis. Now, this is a conventional a 3D printed operation in a typical 3D printing factory. This is an example from China, and you again here on the top left you have a frame-based printer that is operating, and depositing steel layer by layer to produce these 3D printed elements. You have ribs in between the wall that lend it stiffness, right? We need some stiffness against overturning, and that is provided by putting the ribs here. Now, one thing you may notice that you don't fill up the entire area with concrete. There's only some area that is filled with concrete, rest of it is remaining as cavities. Okay. So once such elements are printed, you can see that they are stacked on the side, right? And then they can be stacked in the curing yard of the factory and cured properly until they gain the required strength. Then they can be transported to the site and assembled by jointing between the different modules that you've printed separately. Okay, and then the jointing could be in the vertical fashion or in the horizontal fashion, and this way you can actually complete your structure. The essential difference from precast, of course, this is the same technology as precast in terms of preparing at the factory and then sending to the site. But the primary difference here is that unlike in precast where you need formwork, here you don't need formwork. You're directly printing the desired shape, right? So it saves you a lot of time and perhaps cost in producing a large number of precast objects that can be carried to the site and used for the printing of the structure. So these are some examples of houses that have been 3D printed. This was actually printed on site itself. The left side, you can see the robot sitting inside and printing all around it. So this kind of a telescopic arm robot can be used on site to do the printing. It can sit in a central location and can have access around it. But this is an on-site print, whereas these buildings have come up by off-site prints. Off-site implies similar to the condition I showed you here. The printing is actually done in a factory, and then the printed elements are brought to the site and then assembled. For instance, Vincent Global, a Chinese company, claimed that they printed components for 10 such houses. Like you see the white ones here, 10 such houses, the components for them were printed in a single day. Now, I don't know if the claims are true or not, but you can realize this kind of productivity with 3D printing, and that's quite amazing. There are more examples. This is a example by Icon. You may have seen a recent news item in Google News also, where Icon has used this kind of a technology or this kind of house design to create a cluster of houses in Mexico. You may be able to see that news somewhere. I'll show you a picture also in the next slide. This is again a slightly frivolous use, but of course it's something just to demonstrate the use of 3D printing. So you see here the concrete castle, miniature castle. It's not really a big one, okay? And these are all the elements were 3D printed in this castle. There's no steel involved. It's just concrete. Okay. This is perhaps one of the first commercial buildings printed with 3D printing. It's a Dubai municipal building. And again, it was printed with this robot, which is staying in place and printing all around it. Okay, again, you can see the walls here. The walls have cavities. Okay, the advantage of providing cavities is twofold. One, you can use the cavities to actually insert reinforcement that can be grouted, so you get sufficient lateral resistance. Okay, of course, if you're going for multi-storied housing, then you need to think more about how you should reinforce. If it's a single story, all you need to do is provide minimal reinforcement vertical that can resist the overturning moment in the lateral direction. And this can be provided by maybe reinforcing every third or fourth cavity or so on and so forth. Okay. On the right, you see a cluster of houses printed by Icon. This is exactly what I was talking about from the previous picture. The same type of house. A cluster of these houses have been printed in a village in Mexico, just to demonstrate the power of 3D printing. Now, you may ask, okay, what's the big deal? I can as well do this with a precast operation, especially when you're producing very large scale objects. For instance, I have to produce the walls for 500 houses at a single time. Why don't I rather use precast? You're right. Why don't you rather use precast? The only difference there would be that if, for instance, out of the 500 houses, 500 different owners wanted each house to be customized with respect to their taste or with respect to their wall sizes and shapes and so on and so forth. What do we do then? We can't obviously use precast, because for precast you need to ensure that all your components looks exactly the same. That's something we can achieve now with 3D printing, because 3D printing can help you customize mass housing, especially when it comes to ground story housing or single story housing. You can do a lot with 3D printing. When it comes to multi-story, you start losing the battle at the current stage, because there are not sufficiently good schemes for reinforcing structures which have presented themselves yet, but this is something which will happen eventually in the next few years. Some more description of intricate shapes that you can actually print. To look at the shape of this wall, it almost looks like the interior of a tree. And you can see this one here. These are extremely interesting furniture elements that are 3D printed. This is a bus shelter that is 3D printed. So many different possibilities with 3D printing exist for creating very rapid construction, not just of buildings, but also of accessories. There are more examples here. These are army barracks constructed by the US Army Corps of Engineers. And these are special columns created at ETH Zurich. You can see the kind of shape that has actually been created. This is not something that is possible with conventional construction. You can see this security shed that is being created by Siam Cement Company in Thailand. And again, you can see the kind of intricate design that has been created by 3D printing. I mean, you can't really imagine such things are possible with conventional concrete. These are examples of bridges. For instance, this is a pedestrian bridge that was 3D printed, and this is actually a post-tension girder, segmented girder bridge, which has been printed. These, you can see single segments here. These were printed by 3D printing, and then they were post-tensioned to make this girder and then brought to the site. This is the Netherlands. Now, I've given you examples from all over the world as to how 3D printing has been demonstrated. Mind you, these are all pilot projects. They are not really something which are commercially intended for use in general. Of course, now there is a lot of commercial residential projects also coming up, but there are challenges there. I'll depict what these challenges are in just a minute. Now, of course, with respect to housing, there's a severe shortage in India. We expect that our urban population will grow to 1 billion by 2050. That's a large population. And even as early as 2030, we'll need 100 million houses to satisfy the needs of the urban population. So many of you may be aware, the government of India actually threw open this challenge for builders to come up with rapid means of construction of houses. And this was established by the Global Housing Technology Challenge in 2019, under the purview of which there are 6 different lighthouse projects that have been taken up across the country, where people are demonstrating the use of technology to rapidly construct housing projects. In Chennai also, there is a major housing project coming up where they are using volumetric precast construction for demonstrating mass rapid housing. Now, in this GHTC event in 2019, 3D printing was identified as a potential new technology that may have the potential for revolutionizing the construction industry. And with that effect, the government of India is trying to sponsor some projects to really get 3D printing going in the realistic construction industry. Of course, there's a lot of private investment also that is possible, and people have been coming, although very slowly, to really start putting in more investment into 3D printing to make it happen as a housing technology. Now, why do we want to 3D print houses? I mean, as I already said, precast presents a very good alternative when it comes to mass rapid construction. But at the same time, you cannot do mass customization or individual customization in a mass housing project. And that's where 3D printing can actually do a lot for you. Okay. The other aspect is that you can produce your forms to be structurally efficient. You don't need to go with very solid looking objects anymore. For instance, when you talk about a reinforced concrete beam, that beam does not need to have material everywhere. Okay, there are only some locations where material is actually designed to resist the kind of loading that comes onto the beam. Can we make optimal shapes come out with 3D printing that can be much better in terms of lesser material usage and lesser weight overall, that can improve the performance of the concrete structure? Okay. And again, as I said, you have most of these walls with cavities. So the cavities make it possible to actually conceal your utilities inside. At the same time, you can also do weatherproofing. Heat and soundproofing can be quite nicely done. And the other advantage could be that when you have difficulty in doing construction projects in far off locations where you don't have sufficient infrastructure available, 3D printing could be an option, provided you have at least transportation infrastructure that is built up until a certain distance. Now, the issue is, are we ready for deployment for mass housing projects? Probably not at this stage, because there are several challenges. For instance, how do we automate the reinforcement placement? Right now, it's only manual. People identify where the cavities are, manually place the reinforcement, and then grout it to keep it in position. The finishing processes can be automated also, and there's some work that needs to be done in that regard. You can, of course, do a proper 3D print and then plaster it, but plastering concrete means you're really wasting material. You need not plaster concrete. You can as well finish the surface, and that's where crafting can also be done along with 3D printing. Now, printing is mostly interesting to do for wall elements or column elements. When you start thinking about horizontal elements, it's really a waste of time and money to start printing those. So can we think of a strategy with which these can be made without really wasting too much time in printing the entire element? Because imagine if you have to deposit material over a large area, layer by layer, that will be a time consuming process. So can you adopt a way in which you can print the periphery and put the reinforcement and fill up the remaining area inside with conventional concrete, or even self-compacting concrete for that matter? So that is something that can be done in a rapid fashion, right? The major challenge as far as housing is concerned would be, how do we make our structures comply with building code requirements? Because these are layered materials, right? These are not solid materials. So how do we measure their strengths even? How do we measure other performances like fire resistance, earthquake resistance, and so on and so forth? We need to start creating test methodologies to ensure that these can be measured appropriately. And of course, when you plan utilities, how do we design the optimal plan? And as far as supply chain support is concerned, if you can plan these things and optimize it, you can then get ready for deployment with this technology. There are also, of course, other challenges all over the world. The construction industry is usually risk averse. We don't want to take too much risk as far as construction is concerned. And generally, the construction is driven by cost. They are not driven by interesting alternatives, or rather the cost is also driven by what is actually the cost today for doing the construction. It is not the cost that you require for the complete construction project. Okay, material cost, or sometimes the initial investment cost, some more outweighs any other benefits that you might think about in the long term. So as a result of this, implementing new technology in the construction industry is always a big challenge. And generally, consumers also fear new technology. I mean, people always think, why should I take a risk? Why should I be the first to try out a new technology? So that's obviously a challenge which you need to overcome by proper dissemination. Scaling up requires training several people, including consultants, architects, and practitioners, how to actually work with the material, how to do the design, how to do the construction. All that requires a lot of work in terms of scaling up, and that is still a challenge today. And of course, as I said, lack of data for regulatory approvals How do we actually assess the material? How do we assess the structural components that are built with this material to really make them suitable for use in a construction project? Okay, because how do we satisfy the codal requirements? How do we satisfy the standards and so on? And of course, transportation infrastructure in some areas could be severely lacking, as a result of which, how do we ensure that we can actually transport the 3D printer along with the material to such locations to do the construction? Now, one thing you must note that all the other countries where 3D printing has been successful, such as China, US, Germany, Netherlands, Spain, etc., wherever those major projects I showed you were from, it's driven by the industry. Private industry has come in a big way to drive the construction projects. In India, industry is still not fully into it. They are playing a wait and watch type of a game. If they get in a big way, we can really push this technology to the limit. Okay. Now I'll show you some development of the material as well as the technology in the work that we did over the last 4 years. We started off with a very simple printer. You can see a very small scale printer with a frame here and the gantry, which can move in the 3 axes. Okay, it can move along the 3 axes to do the deposition. This is the first initial nozzle that we had, and these are some of the first shapes that we created. This is with lime-based materials, and this is with clay. Okay, so that's the advantage of 3D printing. Now there's a lot of emphasis around the world on going back to nature, right? While in India we want to move towards concrete, if you go to the Western countries, people want to start thinking about how we can use local soil for doing construction. And 3D printing actually shows a way for doing that. And people have built demonstration structures with local soil itself, which is being 3D printed into the structural shape. And of course, started experimenting with concrete. Now, as I told you, the concrete has to have a special characteristic because you need to push it out of the mold. You need to push it out in the desired shape. It needs to be spread onto the foundation in that desired shape. And when you put the new layer on top of it, it still needs to be fresh enough to ensure that there's sufficient bonding between the layers. Okay, you don't wait for the layer to get hard before you put the next layer. Then there'll be an interfacial problem and you'll have a major failure. So your layers have to be reasonably fresh while the new layers are coming on top. And that requires a very careful control of the rheology of the concrete. Rheology is something which most of us who are in research talk about a lot with special concretes like self-compacting concrete. But here the rheology is a little bit different. In self-compacting concrete, you wanted the material to have a low viscosity and a low yield stress and a high viscosity. In 3D printing, it's just the opposite. You want a high yield stress and low viscosity. High yield stress because you want the material to retain its shape while you print on top of it. At the same time, the material should be less viscous enough to extrude out of the nozzle. So those are characteristics that are quite different from what we are used to as far as self-compacting concrete is concerned. Okay, so here our initial mix design used a binder to aggregate ratio of 40 to 60. You can imagine that's a very large amount of cementitious material in it. And now, of course, we are optimizing this mixture to be able to print with even 25 to 75 binder to aggregate ratio, which is more or less similar to what you have in conventional concrete. Now, target yield stress values are of the range of 1.5 to 3 kilopascals, just to give an indication of normal concrete that is vibrated. Okay, vibrated normal concrete will have a yield stress of around hundreds of pascals. When you talk about self-compacting concrete, the yield stress will be nearly 0 pascal. So here we're talking about 1.5 to 3 kilopascals, which is totally different as compared to SCC or normal concrete. Okay, now you need a rheometer to do the rheological measurements, but we went to the conventional techniques like a vane shear that is typically used in geotechnical engineering to establish the shear stress or yield shear stress of this material. And we use that as the basis for our mix design process. We did several studies to ensure that the mixes that we created were extrudable, right? That means they could be pushed out of the nozzle. Buildable, that means they could be put layer upon layer. They had significant open time. Open time means how long can you work with the concrete? Right? You need that because depending on the type of printer that you have, you may have the printing operation going on continuously. And you don't want your concrete to set inside the printer. That will be a big disaster, right? So you need to ensure that the open time is maintained for a long period of time. And robustness is very important because any small change in material characteristics should not affect the quality of the printed structure. So you see some examples of things printed here with this simple printer with a 30 by 20 millimeter rectangular nozzle. We have this 3-layer wall that is printed, 4-layer wall that is printed. What you can see is each layer rests on top of the other, and you see that there is no deformation of the bottom layers. As the top layer comes on top, the bottom layer is able to retain its shape, and that's a good sign of the right kind of 3D printed material. These were some additional shapes. You can see again square elements that were created with 3D printing, and you see that these layers printing on top do not have such a large effect that the bottom starts deforming. Okay, if your concrete is properly, as you put more dust, the bottom layers will start flowing out. You don't want that to happen. Now, the issue with testing is always a challenging one because in normal concrete, you can always make cubes or cylinders and test the strength. But here, how do you bring in the effect of the interface in there? So you need to probably start thinking about methodologies that are similar more to masonry. Of course, with fresh properties, you can test the flow test. Okay. You can establish the relationship between the flow and the vane shear, the yield stress measured by vane shear, and use that for your design purposes. But with respect to mechanical characteristics, here there's a 4-layered element that is being loaded in progression, and you can see it's a fairly good failure because the material is cracking properly and it's not going through the interface. Okay. Nevertheless, it's important to establish interfacial strength, because of which we went to a much more detailed scheme of characterization where we actually printed such elements which had multiple layers in both directions. And then we extracted samples from these layers. Cubical specimens as well as prismatic specimens were cut out from these layers and then tested to establish the proper material characteristics and the effect of the interface that was there between the layers. So you see here, flexural test is being done for a 2-layered specimen, and you have a proper flexural failure. There's some shifting of this crack at the interface. That means it is moving along the interface to some extent. Here, it's a properly compressed material. You see from the previous picture. Okay, this is the same sort of an object which has been failed in compression. This is actually a test to measure the shear capacity. So what we did was we took a core in this direction. We took a core in this direction of only about 20 millimeters and used that to then create this interface in the middle, and then we did a direct shear test on it to measure the interfacial strength. And this is a pull-off test that is being done for the material to ensure how well it's bonded to the next layer. So there are ways in which you can test it, but none of these are standardized yet. These are just some shapes that we played around with. It's nothing special here. So then from that simple frame-based printer, we moved to a larger frame-based printer, which had a slightly different way of depositing the material. In this case, what we did was we used a pump. Okay, so the material was fed using a primer into the pump. So as the primer pushed, the pump piston basically moved backwards to take in the material. Once all the material was filled up, the piston basically moved forward, and when it moved forward, it started pushing the material into the pipe here, which carried it to the nozzle. Okay, so in one stroke, nearly 75 kilograms of the material could be pushed through the pipe, which carried it to the nozzle, and because of which our printing here was restricted to less than 75 kilos of material at a given time. Why is that? Because when the pump is going backwards, it is not pushing any material into the pipe. So you're basically going to be pushing air in the pipe, and that's a bad thing to do, right? You want the material to be continuously getting pushed into the pipe, just like your conventional concrete pumping operation, right? So here, this is the larger printer. You can see the frame, and you can see the vertical axis and the nozzle attached to the vertical axis. And these are the elements that are getting printed. Okay, these sorts of modular elements, each weighing about 60 kilograms, were printed using this kind of a printer. Now, one thing you must imagine, that when the material is trying to come out of the pump, okay, there's pressure being applied, and that pressure will be dependent on how long this pipe is. The longer the pipe, the more the pressure required for the material to come out of the nozzle, right? If this pressure increases substantially, there's also a danger now of separating the water out of your solid. Your concrete is still fresh, so water may separate out, right? So how do you ensure that that does not happen? You additionally add one more test, which is called the resorptivity test here. What we do is we basically take this concrete and put it inside a cell and apply pressure using a gas, and we see how much water bleeds out. Okay. Less the water bleeding out, the better the concrete is for this operation of pumping. You can see here the pumping being done, material is coming out nicely in a single flow. Okay. You see here the same printer is now being used to actually print the concrete. You see several modules now getting printed. And we essentially ended up printing modules which were nearly 30 centimeters in height, or which had 20 layers of 15 millimeter depth each. Okay. These 30 centimeter modules were then taken to site and then assembled together. I'll show you a picture of the assembly. So here you see the 30 centimeter modules. This is one module. This is one more module. Side by side they are attached, and then one on top of the other you put more and more modules, stack them and join them with masonry mortar. You see mortar is basically used to join them, and sometimes in the horizontal joints we also use textile fabric as reinforcement. And with this we were able to create this kind of a structure, a simple structure. Just to demonstrate the effectiveness of 3D printing, we had personnel visiting from the Ministry of Housing and Urban Affairs, which actually inaugurated this module. We also did a workshop on 3D printing at that point of time, where the Honorable Secretary for Housing had also visited and talked about this technology. We then went on to printing additional elements like these furniture elements, the chair, table, and so on and so forth, just to demonstrate that 3D printing can be an option for printing furniture also, not just printing buildings. You can also produce complicated shapes. For instance, here you can notice that the material is deposited in a slight offset with each layer, and that enables the printing of material which does not need to be supported from below, and that's very crucial if you want to produce architecturally interesting shapes. Okay, for instance, imagine if this were to be used to print a column on the outside, which would produce a very interesting look on the surface. So this is the printer that was then made by Twasta for larger scale printing. With the previous printer that I showed, we could print up to a maximum height of 50 centimeters, not more than that. With this printer, we could go up to a height of about 1.4 meters. Okay, and this was partially sponsored by Larsen & Toubro, L&T, to help us build a toilet module in 2 halves. We were going to print a toilet in 2 halves. Okay. So we had a base slab, the lower half, and then the upper half and the roof slab. All of it were to be printed using this sort of a printer. Okay, so I'll show you more pictures of the printer here. Again, you can see the nozzle in a close-up here. Okay, and here what we did was we had 2 primers and 2 pumps. The advantage was while the material from the primer is getting pushed towards the pump 1 is retracting its piston to fill in the material. At the same time, the pump 2 is actually pushing the material out. Okay, so the tandem pump system ensures that while one pump is getting filled up, the other one is discharging, and then the thing is reversed, and then you have a continuous operation of the pumps possible, which makes it possible to continuously do the printing. And with that, we wanted to print this sort of a toilet module. Okay, and this is the base slab which is getting 3D printed. As you can see here, it's a waste of time, right, to print a horizontal element. Why would you want to fill up such a big area with a single layer and then put one more layer on top and one more layer on top, like what is shown here? There are 5 layers. We wasted a lot of time in doing this. Actually, instead of that, you could just print the periphery and fill up the inside with conventional concrete. Over half of the toilet module coming up slowly, right, in different number of layers. And to see here, the walls were also designed without any filling in between. So this was an empty cavity here. To prevent these 2 outer walls from collapsing outwards, we kept these steel meshes after every 3 or 4 layers to ensure that the walls did not move outwards. Okay. You can see here more clearer depiction of the wall cross section. We also let in pipes to carry the sewage as well as fresh water into the toilet. And this is the fully completed lower half. Okay, this is the fully completed lower half of the toilet, which has the partial entry for the door here. The upper half of was again completed in a second round. So this is the upper half with the roof also that was 3D printed. For the roof, of course, they had to assemble formwork inside and support it from inside to print the roof on top. Okay. Now, the next stage was to actually take this to an industrial scale. So to construct the house that we have on campus today, we had to print the elements on an industrial scale to really get the house construction done in a very fast manner. So here they realized that they could not use the printer to print on simply one bed. Okay, what they had to do was print on multiple beds. So they put the printer on rails. So you see here, there are rails at the bottom. The entire printing setup can be moved along these rails so that the printing can happen on this bed first, then on this bed, and then on this bed. That means they can print 3 times the number of elements in the same amount of time. Okay, and that's what they did. They printed multiple elements which were supposed to be used for the house. Okay, they printed multiple elements, and then these elements were then brought to the site and assembled. And these were assembled in this given fashion to produce the house. Okay, so you can see here, this is one element, this is one more element, and that's the third element. So total height of the print was 4.2 meters. It had to be broken down into 3 different elements for each part of the wall. You can see here, this is a nice curved surface of the wall, and you can see the uniformity of the print quite nicely, right? Of course, the lintels were all precast reinforced concrete lintels. We didn't waste time in printing lintels. Okay? Only things that were printed were the vertical walls in this house. After this printing, we did plastering on the surface so that anybody who sees this house looks at it like a regular house. But for them to ensure that they could still make out the texture of the 3D printed system, we left out certain portions. Like you see here, this patch was left unplastered so that people could actually have a look and feel of the actual structure that is underneath, the type of structure that is underneath, the layered structure. Similarly, when you walk into the interior of the house, you can also see that there are several locations of the wall where the texture of the 3D printed wall has been left as such. Okay, now this house is properly furnished, and of course, this is not the kind of house that we want to build for low-income group housing. This is more of a lavish house because the kind of finishing and furnishing that has been done here is unmatched actually in our campus. We have really created a house that is really beautiful, not like conventional government quarters that we live in. But when we of course adapt this to producing mass housing, and when it gets taken up to a scale where we produce 500-600 such houses through a single printer, then we can start realizing the economy. Currently, of course, many of you may be asking this question, how much did it cost to build this house? Now, with the kind of furnishings and the kind of finishings that we actually ended up doing in this house, the cost is well over 2,500 per square foot. And at that rate, nobody can really afford to build in today's world. But please remember, this is built out of a printer. And this printer, if you use it for multiple numbers of houses, you'll obviously start making up the advantage of reduced cost. If you just print one house with the printer, then there's no point. Okay, you'll not be able to realize the cost advantage. You have to print multiple units. So here there's a single unit that was printed, and despite that, we could still do it with all the finishings at about 2,500 per square foot. We can, given sufficient economy of scale, we can actually bring that cost down to between 1,000 and 1,500. But you may still ask me, what's the advantage then? Because anyway, conventional construction, we can still do it at that rate. Why 3D printing? Why? Because of the time. Construction will take you several months, right? Whereas a house of this size, which 3D printing, this one we did within a period of 21 days, okay? In spite of a cyclone during the construction. We did this house entirely in 21 days. If you can imagine that everything goes well and the production is scaled up to an extent that we can produce components for several houses, right? You can imagine the speed at which this can be done. Technically, within a week, one can get a house completely ready if all the segments have been printed and cured to a sufficient degree, let's say 7 to 14 days to get sufficient strength. Okay, So one can rapidly produce houses at the scale in which one produces cars, for instance, right? It's not, it's pretty much the same because we are manufacturing houses. We are not constructing houses anymore. That's the real advantage of going towards a 3D printed system. So again, in 4 years, we have reached nearly 50% of other 3D printing groups that have been working for more than 10 years around the world. And again, we have reached this at a budget which is less than 1/5 of what other people have spent. And that's because we are constrained in terms of the money. We've not really received any grants for projects. We have not received major industrial grants. L&T gave us a small grant to do the toilet module, but again, much of this work has been executed because of the attractiveness of the technology itself and the way that Twasta as an organization has gone about in inviting people to look at it and also invest some money into it. So the house basically that I showed you was sponsored by Habitat for Humanity, which does a lot of interesting work around the world, and they have actually undertaken this journey along with Twasta to get this technology realized at a commercial level. Now, how to take this forward? The idea would be if you want to do an off-site construction, that means you want to have a 3D printing factory. We call it a micro factory because such factories can be set up within 100 kilometers from each other so that they can serve the needs of a radius of population around them, right? So what happens now is when we create these factories, we create a 3D construction toolbox. The toolbox has the methodology to design very specific elements, let's say straight element, curved element, okay, wavy element. All these things are very well created quite easily by using 3D printing. And what we then do is match these elements to ensure that the architect's needs to build up the specific design can be satisfied, right? So 3D model can be broken down into standardized modules, and these modules can be easily printed and then transported to the site, assembled, and you can then do rapid construction of mass housing, which is individually customized to the needs of the client. That is something you cannot do with any other technology. So again, there's a lot of support that is needed, obviously, R&D support from the industry. And of course, we also are pitching to our alumni to support this in a big way. We can realize these seemingly impossible things like printing toilet modules 6 to 10 hours, printing single story house like the ones I showed you within 5 days or up to a week, printing multi-storied structures in less than a month, and of course also making possible off-the-grid construction in remote locations. For instance, when army needs support in desert areas or in mountainous areas where they cannot do conventional construction, 3D printing may be an answer. We should be, with the right kind of support, mass application ready in 2 years. That should be the time frame we're looking at to really get this technology to a level where it can be mass applied for large amount of construction projects. So just to conclude, this is India's first 3D printed house. Of course, L&T has also built a house in Kanchipuram with 3D printing technology. That was, the 3D printer itself was rented from a company abroad. So L&T has also demonstrated not just a single story, but also a two-storied house. So there is some interest in L&T to develop this technology also. Okay, but this technology that I showed you was totally Indian from start to finish. Everything was done and manufactured here in India. And of course, looking forward to the future, we need to start scaling up and standardizing the production process. During this journey, we have trained a lot of human resources. One PhD student has graduated, one PhD is ongoing, and several dual degree and MTech projects have also been done. There are several journal publications that have already come out, and several more are being prepared at this current stage. So thank you very much for your attention and also encouraging, or rather giving me this opportunity to present before you. I'll be happy to answer any questions that you have. Thank you.
Thank you, sir. Now the session is open to the audience. So if you have any queries, please ask to the professor.
I see one hand raised.
Hello, sir. Good afternoon, sir. I am
Good
MP
afternoon.
Salimanimudan from VIT, sir, research scholar. Sir, I
Yeah.
like to have your view about combining topology optimization with concrete 3D printing or other digital fabrication techniques, sir.
Okay. Now, obviously, that's a major scope of research today. If you look at many of the 3D printing articles that come out in papers, topology optimization is the challenge that people are taking up in a big way. Especially structural engineers are interested in looking at that particular option to see how well we can optimize the kind of shapes that we are printing. Yeah, and that's definitely an area of research that has tremendous potential.
Thank you so much. Thank you.
Good afternoon, sir.
Good afternoon.
Sir, you will be showing the house which is constructed at IIT Madras campus, and you went for part by part module for construction. Then how the joint process will happen, and
Yeah, so here the
how the
jointing
joint will.
was, yeah, jointing was done by simple mortar-based joints. Okay, so there's no complications there with a single story structure. You can always have a mortar-based joint between the modules to get it functioning well together. But this is not optimal because the joint can end up being the weaker plane, right? And be the cause of not just strength-related issues but also durability-related issues. So we are working on the concept of actually not having such vertical joints which could provide to be weaker planes, but rather come up with design of modules that can sort of lock into each other while creating minimal direct vertical joints. So that is something we are working on.
Sir, apart from the budget and the skill labor, what are all the other challenges this technology should address, sir? Apart
Apart from
from
what?
labor and cost.
No, of course. See, truly speaking, this technology should minimize the use of labor, right? Ultimately, we should be able to do printing like a manufacturing operation. That means having minimal number of people around. Okay. Now that can be made possible by ensuring that you have a mixture that can be prepared without much human intervention, by having a system that works at a click of a button. Ultimately, that's what is needed. Otherwise, this technology will prove to be too expensive. If we have too many people around, uh, checking at every step of the process, that'll be a problem. So as of now, of course, the kind of operation that we are doing here requires the use of a lot of people, but we are trying to get it to the stage where there's a lot of confidence in the system handling itself rather than people coming in between.
Good afternoon, sir. This is Malati. Thank
Hi.
you so much, sir, for accepting our invitation,
Welcome.
for giving this wonderful presentation on 3D printing, sir. One clarification is, sir, suppose if we want to give a small project to our students on developing some eco-friendly 3D printing material or concrete mix, how we can do it without 3D printer? Is it possible to fabricate a small prototype printer so that it can give a pressure, the same pressure the material will extrude out of it, so that we can test its rheological properties and the hardened properties also?
Oh, yeah, this is a very good question. Now, see, there are different ways of looking at it. One, if you think that 3D printing is going to be a major part of your research efforts for at least 3 to 4 years, then it makes some sense in actually buying at least the smaller scale printer. The one I showed you previously, I think some investment into setting up the smaller scale printer would be useful. Or even the second stage printer that I showed you, that the one which used a pump and pressurized the concrete into flowing out of the nozzle. That kind of a printer you can purchase for around 30 to 40 lakhs would be my guess. I'm not very sure, uh, but if you were more interested in the material itself and not really worried about thinking about printing in the long run, then there are alternative ways of actually designing your own printing strategies. For instance, if you look at literature, they are using extruders. So extruder is nothing but a hollow tube into which you put your material, and then there's a piston which pushes the material, and there's a nozzle at the bottom. Uh, that, of course, has its own limitations, but still, for a starter, that extruder will be a good way to actually test your material. Of course, after you've done all the other tests, for instance, after you've established rheological characteristics. If you don't have a rheometer, as I said, you can use a vein shear apparatus, which is commonly used in geotechnical engineering for soils. You can use that to establish the yield stress parameters. You can use flow table testing, or you can use other viscosity measures to determine the other rheological characteristics of the 3D printed material. So you can do all of that, and you can also obviously determine the strength of the material itself by casting it into molds. But if you really want the assessment of the layered strength, then you have to obviously extrude. And this type of an extruder you can fabricate easily into your workshop. You don't need to really buy a printer for that purpose. Only problem with the extruder is that it's not really properly capturing the actual process of printing, which involves, of course, pushing the material, making it flow through the pipe, and then coming out of the nozzle. So extruder basically just pushes it and directly comes out of the nozzle. So depends on what you'd like to do. If you want to invest, this will be a good opportunity to invest, because there are printers available that can satisfy your needs in that budget. If you're looking for a larger scale investment, of course, buying industrial scale printer is always a better option, because then you can really test the technology at the larger element level, which is important from establishing its performance for a real structure. In those cases, the last stage printer that I showed you, that's the kind of printer you should invest in. But that's not really an R&D printer. It's more intended to simulate real life printing situations. But yeah, you can connect with Vasta. If you really have specific needs, I can help you connect with them to maybe even establish a small printing facility in your laboratory.
Thank you so much, sir. Actually, we have got tie-up with this IIT incubation, sir.
Okay.
In that, we have signed MOU also
from
Sona. If it is possible to guide us regarding that 3D printing platform, can we set? It will be good for us, so that we can do some initial research and first starters, as you mentioned. Sir. Thank you, sir. Thank you so much, sir.
Welcome.
Suppose to the site, how to bring those 3D printers, sir, through the containers or
the printer that I showed you in the end, the larger size printer, that is completely dismantleable. You can dismantle the entire thing and assemble that again.
Okay.
So that's not really a problem, because here also they created the printer in Bangalore, and they dismantled it and then they brought it to Chennai and then assembled it. It doesn't take them much time to do that.
Okay, sir. Thank you so much, sir.
Krishnan sir, you can ask the question.
Yes, ma'am. Am I audible, ma'am?
Yes.
Yes, sir. So very good morning, sir.
Morning.
This is Krishnan from Knowledge Institute of Technology, working as assistant professor. It's really a good session and with very deep inputs with respect to 3D printing, sir. So I have one query. With respect to CAST Institute testing, likewise in the conventional procedures, at the moment of casting or pouring the concrete, we can do some slump cone test or some workability test. So likewise, any methods of testing is available for this 3D printing, since the materials are already formed manner. So whether how can we check the tensile or the compression properties? So in that aspect, I have a query, sir.
No, so with respect to the fresh properties, similar to the slump test that you do for conventional concrete, and 3D printed concrete, you can do the flow table test. The flow table test can be done. Either if you're using small scale aggregate, you can use the mortar flow table test. If you're using larger scale aggregate, you can use the concrete flow table test. So that's possible. Establishing a fresh properties, it's not that difficult, except that, of course, you need to understand what fresh properties are desired. For that, you need to get a clear picture of how this flow table value is related to your yield stress and viscosity. That has to be obtained through a regular research and development type approach. Now, you can control the quality in the fresh state with the flow table test. In the hardened state, similar to testing cubes or cylinders, we don't have a direct means of understanding what is the strength of the 3D printed layered system. The 3D printed material you can as well cast into a cube and cylinder and assess the strength. But for a layered material, how do you assess the strength? And that is something which people are still trying to address through an appropriate testing scheme. How to prepare the specimen itself is a question. Whether you need to do printing or you need to do printing of the specimen for its exact size, or you print a larger specimen and then cut it out of that. All these are subjects of debate right now. People are trying to grapple this particular important aspect now, and I'm sure that in the next few months you'll have a much more better picture of that. Right now there is no conventional standardized test method for this. Yes.
So I have one more query. May I ask, sir?
Sure.
Sir, for assessing the crack width and the depth of a specimen, nowadays chips, embedded sensor type chips are available. Can you suggest any particular chip varieties like impedance chip or like that for assessing the or measuring the depth and the width of the crack in a concrete member?
Well, I'm not aware of sensors to measure the characteristics of the crack. Sensors can detect the formation of a crack. I don't know how sensors would measure the size of the crack inside the concrete. I'm not sure. Externally, of course, you can measure the crack width quite easily by using crack width microscopes, but crack depth, establishing crack depth is not an easy proposition. It's not easy. I mean, there is no well-defined technique that can do that. Yeah, I mean, people talk about using ultrasonic methods and so on, but it's like fraught with errors. You can't really do a good job with it. But crack width, of course, you can establish. That's not a problem. Visual plus you can do a microscope-based assessment.
Okay, sir. Thank you, sir. Thank you for the opportunity.
Welcome.
Shalini, is there any question in chat box, ma'am?
No, ma'am.
Yeah, I don't see any questions.
Sir, but from from student side, I got a message from WhatsApp. So they are asking you what are the failures and the problems you have faced during installation in IIT Madras.
Okay, it's a good question because a lot of the effort in printing depends on how successful you are with printing. What I've shown you is only the successful prints. Behind each successful print, there was at least one or two failure prints which had failures also. How does the failure come about? Okay, there are two distinct ways in which you can see failure in freshly printed concrete. Okay, of course, I didn't plan my presentation towards that, but yeah. So you print layer upon layer, right? And if the layer below has yield stress that is quite low, what will happen is as you print layer upon layer, the mass of the upper layers is going to bear on the lower layer and cause it to start spreading out. So that's actually a failure because your wall is no longer having a uniform dimension. The lower half of the wall has started spreading out. Okay, so that's not a good thing to do with 3D printing. You need to ensure that such failure does not happen. Second is when you're printing layer upon layer, as you're reaching a particular height, there's a chance of what we call self-buckling. Okay, so you know that this is a slender layer that we are printing, slender wall that we are printing one on top of the other, and there's a chance that your entire set of layers may start buckling or toppling over to one side. That is also another failure that often happens in 3D printing. And these kinds of failures need to be very carefully designed and understood. And there are theoretical concepts that can be applied to really understand how to reduce this kind of failure by controlling material characteristics properly. These are the two normal failures that you expect in fresh concrete. Now, of course, if you don't correct for these failures, if some of these get built into the structure, for instance, if you're not printing the layers right on top of each other and there's a small displacement, right, your entire wall itself will be slightly curved. And that will also show up in the resistance of the wall to the loading when it's hardened. Right, the material won't change. Material is still the same, but the wall itself, because it's not perfectly straight, right? It will be loaded from the top and there'll be eccentricity in the loading that will cause the wall to fail at a lower load as compared to what it would if it were perfectly printed. So printing conformity is very important. So geometrical conformity is extremely important. If you don't do a good job of doing that, you'll end up having a problem of failures. So there's a lot of failures that happen. You can actually see several videos that show you different types of failures that can actually happen with 3D printing.
Thank you, sir. And some more questions in chat box.
Yeah, I'm seeing that somebody that asked about design consideration. Okay, now design consideration is something that is yet to be totally worked out. You can obviously design the concrete walls and design the section of the wall to resist the load that is coming onto the top, right? If you need to resist axial load, the concrete itself is enough. If you need to resist lateral load, then obviously you need to ensure that you put steel in at least every third or fourth cavity to resist that lateral load. So design can be done similar to a conventional wall or a conventional column. Okay, but then still the aspect of design and testing of the material quality for meeting the design requirements, that is still a subject of much research. Is there any assumption for the width of the layer? There is no assumption as such. The width of the layer is just decided upon based upon the nozzle size that you have and what nozzle size would be required to produce a stable configuration. If you want to print very fine components, then obviously the width of the layer will be very small, right? If you want to print very stable components, you can increase the width of the layer. That means your nozzle opening also is larger. So you have to design your material and the printing strategy to suit the kind of application that you're doing. Which material is used for 3D printing? Concrete, of course. We are using concrete here. This is construction 3D printing. We are using concrete. Which type of industry used 3D printing? Of course, I'm talking only about construction, so I'm not sure what your question means here. Yeah, what are the materials used for concrete mix to get that flowability? So here, please remember, we need the flowability to ensure that the concrete comes out of the nozzle, but at the same time, it should not be so flowable that when you place it in the given location, it starts flowing outwards. We don't want it to do that. We want it to maintain its shape when we press it out and put it down on the structure. Right, for that, we need to have a combination of chemical additives. So in the mix that I showed you, we had cement, of course, fly ash, we had sand, which was carefully graded to ensure that we had the right particle sizes in there. We use polypropylene fibers to ensure that the cracking in a fresh state, plastic shrinkage cracking and drying shrinkage cracking could be avoided. Then we used chemical admixtures like super plasticizer to ensure that we had the required flowability. We use viscosity modifying agent VMA to ensure that it retained its shape after printing. Okay, and sometimes we may also need an accelerator to ensure that it maintains the shape even after the next layer comes on top of it. So there's a complicated design as far as the material characteristics are concerned. You need to have multiple chemical admixtures to ensure that you are able to control your characteristics of the concrete to the level that you want. Okay. Many research papers will give you the entire set of details about what materials are used, how much of these materials to use, and so on. In fact, when we started our research studies, we also adopted the mix based on some suggestions from research papers. You don't have to start from scratch. You can always, that's the idea of reading research papers, to really get an estimate of what others have done and how do you actually try to focus your efforts from that point onwards to improve the conditions that is already existing. Yeah, I think that's all with the questions in the chat box.
Sir, Oscar sir question is like elective, which industry is using 3D printing technology?
I'm not able to understand that question because we are talking about construction industry, no? So what type of industry implies what?
Okay, sir. So can we use a reinforcement in 3D?
That's what I was saying, that
One more
integrating reinforcement inside the structure while doing the printing can be a big challenge, right? Because how do you print, because if you put a reinforcement and then try to print around it, that will be like a blockage, right? You don't know how your printer will move and so on and so forth. So in most of the cases that I showed you, the wall was printed with cavities and the reinforcement was introduced manually, right? So automation of reinforcement placement remains a big challenge. Okay, I think there's a question on flow range for concrete in 3D. As I said, concrete should not flow. Okay, flow table test has to be done. So when you actually do the test and remove the outer cone, the concrete should not flow on its own, but it should flow when you actually do the dropping of the table several times. So you need to ensure that your concrete has that kind of a characteristic. Coarse aggregate size used for the mix. Here, no coarse aggregate was used for the mix that I showed you for the printing of the house. We used only sand with a maximum size of 2 millimeters. But we've also printed using coarse aggregates of size up to 8 millimeters. But that requires a much stricter control in the quality of the mix. Because please remember, when you put coarse aggregates, your concrete becomes heterogeneous. And controlling the concrete quality for proper extrudability and buildability is very difficult when you do coarse aggregate based printing. Most of the world that you see the examples of 3D printed structures, they are with fine aggregate only because of the consistency with which you can print. But that doesn't mean you can't print with coarse aggregate, you can. The design period of the 3D printed building same as normal building or different? Of course, for this building, we didn't take much time to design the construction and understanding how to do the construction with the different modules. That required some time, that's all. What type of software analysis is done prior to the process in concrete 3D printing? If you are associating it with the design, the same type of design software should be used to assess the characteristics of the material and thickness and dimensions that you require to resist the loading. No difference there. But as far as the printing itself is concerned, of course, printing involves the use of a software which is sometimes freely available, right? If you're a Unix user or Linux user, the software is freely available. And sometimes people who do 3D printing develop their own versions of the software to convert 3D models into printable layers. And that's what the software basically does. It converts a 3D model into a printable layer. Limitations for 3D printers, well, there are many limitations. Of course, as I said, printing with coarse aggregate is a limitation. Printing around blockages could be a limitation because you have to have a nozzle which has access properly around the blockage and so on. You need to ensure that the material is supplied continuously to the nozzle, otherwise there'll be gaps in printing. You don't want that to happen. So, of course, there are limitations. You need to design your strategy of printing to overcome these limitations. Right? Any other questions?
Yes, sir.
Yeah.
So no more questions in chat box, sir.
Sure. Of course, you can also write to me by email in case you have specific questions. If you can't think of them right now, and you can review the material and then come back later. There's a lot of papers I urge you to read if you're interested in this subject. In fact, there's a lot of content available on websites also, and there is tons of videos on YouTube showing 3D printing being done. So,
Participant, do you have any queries? You can ask or post a question in the chat box.
my mail ID was already shared in the presentation. Maybe I can write here itself. Yeah, I've shared my mail ID. How can we provide staircase in case we construct more than a single story? Those are elements that you need to provide separately, just like you do in a conventional construction project. You can always print a staircase also and put it in place. It's not really a problem.
Ma'am, HOD ma'am. Thank you, sir. I think the questions was over, sir. If any other questions are asked, I will send you mails, sir.
Yeah.
I'll consolidate and send you mails, sir.
Okay. Thank you then.
Thank you so much, sir. We are very much delightful for having a speaker like you in our FEP, sir. And it was an eye-opener, and we all came to know new technology which is going to rule our construction industry in future. So I hope we all of them have enjoyed and understood well on this technology, and definitely we try to implement this new technology in our working area, sir. Thank you so much for your deep input and wonderful section ahead, sir. Ma'am, HOD ma'am.
Thank you, sir. Thank you so much, sir, for your excellent presentation and input towards 3D printing, and also patiently replying for all the queries and questions, sir. Thank you so much, sir, for your time and effort. Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
So
I'll
much.
leave it. Thanks. Thank you.
Okay, thanks. Dear participants, the session was over. Thank you for your attention and patience. The next session will be start at 2 p.m. 2 p.m. and no feedback link. So the feedback link will be posted at 3:30 p.m. So thank you all. Now it's time for lunch. So please all join at the correct time. Best question and answer session till now. Thank you, sir.